Aha, that's better. Here we are. Okay, cool. I'll just give it maybe a couple more minutes for a few extra people to join. Okay, I think we can maybe make a start. So, hi everyone, thank you for joining. My name is Paul. I'm one of the co-leads of the IAVCEI Commission on Tephra Hazard Modelling. And I'm delighted that today we have both Kadek and Susanna here who are going to give us a pair of talks. Before we get started, I'm just going to show a few slides to present basically a bit of an update on some upcoming Commission activities. And then I will introduce our two speakers and we'll get cracking. So, if I just... So hopefully you can all see my screen. Just before we get started, I'd just like to bring your attention to some Tephra Hazard Modelling sponsored sessions coming up next year's IAVCEI conference, which abstract submission is now open for. We've got dynamics of volcanic eruption plumes, the role of water in explosive eruptions and their products, and also operational hazard forecasts, source parameters, and model evaluation. We're also sponsoring some workshops at IAVCEI. The top one here is Volcanic Ash, strengthening the connection between operational response and research, a volcanic plume benchmarking exercise, and also a workshop on grain size analysis of volcanic ash. So abstract submissions are currently open, I think, until the 20th of December. And registration, I think, for workshops is also open as well. If you have any questions about any of those sessions or workshops, feel free to drop me an email and I can forward that to the relevant session or workshop organizers. So just a quick introduction to this seminar series. So we host this series, which we call Ashvances on Tephra Hazard Modelling. Alistair, one of our other co-leads, is very proud of that particular pun. We aim to hold seminars about every 3 months. We've had a bit of a gap since the last one of these. We actually did that probably closer to 6 months ago, but the aim is every 3 months. 2 speakers each time, each with a 15 to 20-minute talk, and we aim to allow 5 to 10 minutes for questions. Hopefully some time at the end for some general discussion. We do try to rotate our time zone for the seminars between different times, friendly times for across the world. But we do record all the seminars so that everyone can watch, even if the talk is being given in the middle of the night for them. We particularly want to showcase research from scientists from underrepresented groups. And so if you are interested, you can use this QR code here to register or even nominate someone who you think would give an excellent talk. So please follow that option if that would interest you. Other news, we are planning on hosting or organizing an upcoming special publication on Tephra Hazard Modelling. This is being organized by Alistair Hodgetts, who is one of our co-leads. I've realized I've missed a slide, but I'll come back to that. And themes in this are limited, can include, but are not limited to field studies, modeling, reconstruction of past events, or forecasting. If you're interested in being involved in this, please drop us an email at this address here with a proposed title, or that can change, and we'll be in touch with more information. I realized I missed a slide, so I'm actually don't know how that happened. It's not coming up. Oh, okay. This is the slide I missed. Apologies. Basically, you can use either of these QR codes to subscribe to our mailing list, or check out our website. And just to introduce our other commission leads alongside myself, we have Alistair at the University of Edinburgh in the UK and Thomas, who's at the University of Exeter. So among the things the commission does is our aim is to foster communication and collaboration between volcanologists who have a broad range of disciplines, but an overall interest in Tephra Hazard Modelling. Organize seminars such as this, but also workshops, symposia, and field trips. And we also aim to support working groups investigating Tephra-related processes and impacts. Anyway, moving on to today. We have two speakers today. First up will be Kadek Sumaja, who is from the Indonesian Agency for Meteorology, Climatology and Geophysics, as well as UNSW Sydney. And he will be talking about volcanic ash risk map and adaptation plans for Indonesian Aviation Services. We'll then have Susanna Jenkins from Nanyang Technological University, Singapore, talking about building damage from Tephra falls. What can we learn from empirical data? So I'd like to hand over to Kadek to get us kicking off. So Kadek, feel free to share your screen and get going.
Okay, thank you, Paul. Yeah, try to share my screen. Okay, everybody, can you see my screen?
We can, yeah.
Yeah, okay, cool. Okay, thank you, everyone, for the wonderful opportunity. My name is Kadek Sumaja. I am an aviation meteorologist. I'm from School of Aviation, UNSW Sydney. My research focus is in the assessing hazard and risk and developing resilient plan in aviation sector that related to climate risk or climate change. Therefore, I would in this talk I would discuss a type of Tephra hazard according to perspective of meteorologists, climatologists, or in aviation. So in this talk, my topic about the volcanic ash risk map and mitigation plan from Indonesian Aviation Services. I'm studying in Bali Aerospace. And the specific almost 30% of the world's total volcano, and more than half of them are classified as highly active and having erupted several times since centuries ago. And Bali as one of the most favorite tourist destination in Australia. Tourism also unfortunate because it's near the three active volcanoes. In this is Bali location. There are three active volcanoes here, and because the dispersal of volcanic ash in the atmosphere can cause a significant risk to our aviation service because it can damage the engine or make a compromise to our avionic and navigation system. Also, according to history, there are some major closure of airspace during volcanic ash eruption in several locations in the world that show that this aviation sector is really vulnerable to volcano activity, specifically in volcanic ash, because the volcanic ash can stay in the atmosphere for hour and day and make our service disrupt our service, causing flight delay, cancellation, and significant economic loss directly or indirectly. Because it's often forcing the airport and service to close. And despite we have try to predict or make a warning before that, but still lack of preparedness or mitigation plan. I want to emphasize what's the climate factor that influence the volcanic ash. First of all is precipitation as well as humidity and cloud, because volcanic ash can act as a cloud condensation nuclei, as a cloud can either trap the ash particle and make them as the nuclei of their condensation, so it can make it wash away from the atmosphere, like what the rain or precipitation do, because they can instantly removing the volcanic ash from the atmosphere, depend on the intensity of the rain or precipitation itself. Secondly, the wind. Wind is one of play important role in dictate the direction and distance of volcanic ash, because it can make the volcanic ash travel either they close to the airspace or either quite far away from the airspace, depend on their speed and their direction. And the temperature gradient or thermal convection, it can enhance the transport of volcanic ash to the higher altitude. Using the thermal convection energy, they can uplift the particle of volcanic ash to the very high or upper atmosphere, and the prevailing wind can wash it away from that location. And atmospheric turbulence can cause a random, unpredictable movement of volcanic ash, affecting its concentration and distribution. This is the map of our airspace. This is Bali Island, and this is Bali Airport. There are three near active volcano here, Mount Raung, Mount Agung, and Mount Rinjani. And this is our airport, only have one single runway, in runway 09 in the west and runway 27 in the east. That runway is very dependent on the wind direction to determine which runway we're going to use. And wind as well also can influence the movement or direction of the volcanic ash from volcano that near that early airport. That's why I would like to try to build a risk map by combining various data here. For instance, using the 24 data we collect from 24 observation point that spread all around the Bali, using 30 years wind data in the several elevation. I'm gonna tell you several elevation like this. In aviation industry, we call it a flight level, from flight level 50 to flight level 550. Level 50 mean the elevation is 5,000 feet until the 55,000 feet. We use the wind direction in the several level here, and combining the flight route data, rainfall in every season from January to the December during the 30-year period, 1991 to 2020. And in this model, we only utilize two climate conditions, that is rainfall, monthly rainfall, and average wind data, without considering the eruption source parameter and without considering the total grain size distribution. How do we process the data here? From the wind, we categorize them into two classes. Like the wind that direction toward the Bali airspace, we categorize it as a high risk. We give the rank 3 to 4 because it has possibility to carry out the volcanic ash toward our airspace. And direction opposite Bali airspace, we categorize it as low risk from 1 until 2 rank level. Secondly, the monthly rainfall, based on Indonesian Agency for Meteorology and Climatology, we categorize them into 4 ranks. It is low, intermediate, high, and very high. From low, we rank them as a 4 because the low intensity of rainfall has a low possibility to catch the volcanic ash in the atmosphere, low possibility to wash them away. Meanwhile, when when the intensity of monthly rainfall is very high, we categorize them into the low risk because they have a high opportunity to wash away the volcanic ash in the atmosphere. We use equal weighting here without doing any specific weighting. We just use equal weighting here. Then we just sum up a rating of the wind and rating from the rainfall, created a risk level. Risk level we classified into 4, like no risk, low risk, medium, and high. For instance, from the no risk, if we consider that the wind direction move to opposite of the Bali airspace, the risk maybe 1 or 2, very low. If the rainfall is very high, also the risk is low here. So the sum up of them can result in the number or 2. Also happen in the high risk here, if the wind move toward our airspace and there is no rain or the rain is quite low, it can pose a high risk possibility in our airspace. This is the Bali airspace. This is a terminal maneuvering area from level 100, from flight level 100 or 10,000 feet to 250 to or 25,000 feet. This is the location of our airspace where the aircraft come to our area. This is the Mount Raung here. This is our airport, Mount Agung, and this is Mount Barujari. They are also inside our airspace terminal maneuvering area. So we will focus our analysis here of the risk map or risk category from flight level 100 and 250. Before that, I will tell you about the three volcanoes that erupt and disturb our surface here. Start from Mount Raung. Yeah, Mount Raung located in the western part of our airport. It's the stratovolcano erupted in July 2015. It make our airport close. From the volcanic ash advisory center, we can see the volcanic ash coverage here almost cover all of our airspace here. In the June, yeah, volcanic airspace here, and in the July 2015, we can see this is the movement of the volcanic ash from satellite image from Himalaya satellite that move toward our airspace here. Secondly is Mount Agung. It's quite close to our airport, around 50 to 55 kilometers in the straight line from our airport. It's located in the Bali, Indonesia. It's since the last decade is erupted twice in November 2017 and June 2018. Make our service in Gusti Ngurah Rai Airport also closed. This is volcanic ash coverage from from the map. We can see that the movement or the coverage of volcanic ash from the Mount Agung almost cover also our airspace and also our airport here. Unless in the last these years, from the satellite, we can see the movement of volcanic ash here. They move toward our airspace and our airport. That make our airport close as well. Lastly is the Mount Rinjani. To be specific, is the Barujari, is the baby volcano in the Mount Rinjani crater. It's erupted in November 2015, also caused our airport closed. It's a stratovolcano as well. And this is the coverage of volcanic ash is cover almost our airspace because it's moved to the west to our airspace area as well as our airport. This is the image from satellite of the movement and coverage of volcanic ash from the Mount Barujari or Rinjani is moved directly toward our airport and almost cover entirely our airspace. The result that what would like to discuss, this is the graph from 24 observation point from January to December. We divide it into three graphs for its flight level. The blue mean no risk, orange mean low, gray mean medium, and yellow mean high. From the Mount Raung, we can see here in the three flight level, it has a high possibility of risk in December, January, February, and March because Mount Raung Mount Raung is located in the western part of our airport. During this season, December to March, is the western monsoonal season. So the wind mostly tend to blow from the west to the east. They carry the volcanic ash to our airport. This, I think, that's make the possibility quite high here. But in April and November, it's quite low, or there are some medium in June, July, August, and September, because even though the wind is still fluctuative during that season, and the eastern wind start to blow, but during this season is a dry season in Bali and surrounding area. So it's reduced the possibility of rain to wash away the volcanic ash in the atmosphere. In terms of Rinjani and Mount Agung, the graph almost similar, because the high possibility of risk mostly occur in more than in 24 observation point in April until October, or some case in Agung until November, because during this season, there's the dry season is occur, and the wind, there are easter monsoon occur happen that blow the volcanic ash from their location in the eastern part of Bali to the west. So the wind blow from the east to the west, carry the large amount of volcanic ash. If in that, so during this month, the very high, but during December and January, the wind blow from the west, that causing the low risk of volcanic ash exposure in Bali and Bali airspace. The same pattern also occur in the different flag level, only the number or the proportion of the high, medium, and low is different, but still the pattern of this month is quite similar here from Raung, Agung, and Rinjani. Secondly, before I show you the risk map here, I would like to show you about the takeoff and landing chart here, because this is the one of the most important activity in our airport. In this airport, during the takeoff and landing activity, in runway 09 and runway 27 during arrival, when the flight coming in our airspace, mostly do it in the flight level 130 or around or below. Also during the departure, also flight level 130 or below. That's why I would show you the risk map in Bali area that close to the flight level 130. That data that we can collect is on the flight level 140 here. The risk level in the Mount Raung, when Mount Raung erupted, it would be pose a high risk that show in the map as a red here. If they erupted in January, February, May, or October, it would like pose the high risk in our area here. In December, January, and February, they almost cover entire of Bali airspace, mostly cover the airport that located here. So during this season, October, January, and February, if the Mount Raung erupted, it will cause will give a disastrous impact to our operation in the airport, because we have no chance to, most likely we would like to close our airport if erupted in during January, February, and March. However, when they erupted in May, even though it's cover most of Bali area, but it's still like a medium chance to cover our airport. So we can alternate our flight route here, so they can do some takeoff and landing using this area in the eastern part of the red zone here. On the other hand, the risk pose is quite low here, quite medium until low. In terms of Mount Agung, sorry, they pose a high risk from April to November. Even though they mostly cover our airspace, but they still pose only medium risk in our airport here. So we can do some alternative or alter our flight route here, so they can avoid or evade the high risk area here. However, if they erupted in December, January, February, and March, it's most likely the ash will reach our airport, like you see in the map here. even though in the north part of area is still medium and low risk, but our airport here would most likely experience the high risk level impact of volcanic ash itself. It's most likely we should close our airport if they erupt during December, January, and February. But otherwise, in other month, if they are erupted in other month, we can do some another plan or mitigation here. Even though it's still medium, we can do temporarily close or temporarily open our airspace or our airport. If the
Sorry, Kadek, just to interrupt, you got about 5 minutes left.
Okay.
Is that okay?
Okay. It's almost finished. Okay. In Rinjani volcano, from April to November, they almost cover our entire airspace, mostly in our airport here. We can most likely we're gonna close our airport, but during December we can do temporarily. In January, February, and March, if the Rinjani erupted in this season, the risk that they pose is quite low because the wind is blow from the west, is quite blew away the volcanic ash from Rinjani in opposite direction toward our airport. Some adaptive strategies is we can do like a probabilistic risk assessment, like using a probabilistic approach, like projection in the future using the risk map that I haven't finished doing it yet because using the numerical model or climate projection to do a projection of risk map in the future. Maybe later if I finish, I can share again with you. This is some kind of strategy. I also refrain from Susanna work here about in the Southeast Asia about the level of exposure of the volcano. This strategy also enhanced by wind detection using Doppler wind lidar or projection in the future. And we can enhance the monitoring and early warning, implementing the monitoring system for volcanic activity by integrate them with early warning system, either for weather or volcanic activity watch, and provide the timely alert for aviation authority. Thirdly, like I explained before about the flexible air traffic management, like we can do flight traffic management strategy, like concept to avoid flight path through the region with high volcanic ash concentration, alter their flight route, and combine using a warning and probabilistic risk assessment, we can make a better alternate flight route here. And lastly, we can do a collaboration or flight planning response between airport stakeholder or volcanologists or meteorologists to build a better risk assessment or risk resilient plan. And conclusion, in volcanic ash in Rome volcano, most likely exports risk in Bali airspace from flight level 10 to 180 if they erupted in December, January, and February. And in Agung volcano, from flight level 50 to 180 if they erupted in May, June, July, August, September. Meanwhile, in flight level 240, it will generate a high risk in March and December. In terms of Rinjani, also the same from flight level 10 to 150 from May to November, but from flight level 240 expose high risk almost every month, especially flight level 30. And lastly, the adaptive strategies to mitigate volcanic ash. We could include the combination of probabilistic risk assessment, monitoring early warning, flexible air traffic management with collaborative planning and response. This is a reference. Okay, thank you. That's all, Paul.
It's the end of my presentation.
Okay, that's the end of my presentation. Thank you.
Cool. Thank you very much, Kadek. That was really, really useful and very interesting. Maybe just because of my technical issues at the start, we was a bit slow getting started. So maybe what we will do is we'll do Susanna's talk and then we'll do questions collectively for both yourself and Susanna at the end. Is that okay with you?
Yeah, that's okay. Cool.
Cool. Okay, Susanna, are you happy to go ahead and share?
Yes. Is it shared?
Cool. Yep, that's visible and we can hear you too. So
all right, good. Okay, thank you for the invite. Too many screens open. There we go. Thanks for the invite, for giving this talk. I'm going to follow on with the theme of impacts. but I'm going to be talking about tephra fall as opposed to airborne tephra, and I'll have a focus on buildings just to keep this tractable within the next 20 minutes or so. This is a beautiful image, not mine, unfortunately, but it's Calbuco eruption in Chile in 2015, and you can see the ashfall plume going away from us in this instance. And as we all know, a change in wind conditions would bring that ash plume over this densely populated area here. And in fact, there was quite a lot of damage from this eruption in 2015 anyway. Okay, so preaching to the converted, I suspect, but one of the most interesting things for me, I think, from the tephra fall impacts is that it's really quite a wide range of potential impacts, and it can cover a really, really large area. Just as we heard from Kadek, we have potential closure of airspaces at sometimes thousands of kilometers around from the volcano. And this is a plot, a schematic we made for the UN Global Assessment Report more than 10 years ago now. But on the x-axis, we have distance, and on the y, we sort of have hazard, but it's a schematic. So on these distal areas, we have more nuisance effects from tephra fall. You know, might be a bit of cleanup. There's obviously an effect on aviation, as we just heard. And as we move towards the volcano, as the tephra fall becomes thicker, then we see more significant impacts. Mostly there's cleanup in all of these areas, but we can see impacts on crops and livestock. This is someone falling off their roof from cleanup, so we see incidental associated impacts as well. We know that about 3 millimeters of moist ash can actually cause insulator flashover, so we can knock out an electricity network. And then as we move further towards the volcano in the proximal areas, we can really see complete destruction because of the weight of the ash or tephra on roofs, on vegetation, on other infrastructure. And at these areas where we have a lot of ash, then we can see knock-on impacts of, for example, wastewater treatment plants, where mechanical aspects of the network can be ground down by the amount of ash that's being washed into the system. And so how do we forecast these impacts or learn to mitigate them? Well, we need to know more about them. So any good geoscientist knows that the past is the key to the future. And so we really need to know what impacts have looked like in the past to be able to forecast what they're going to be in the future. This is a study from Natalia Deline and others from a couple of years ago. And it's basically looking at the whole impact assessment field. And it's for all volcanic hazards, not just tephra fall in this instance. And we're looking at the number of studies that have been published on impacts, volcanic impacts, and it starts in 1980. So prior to Mount St. Helens 1980, not a single thing was published about the impacts of volcanic hazards, which is quite phenomenal, I think. And if we look at impact studies across this last 40 or 50 years, 50% of the studies have been published only in the last 7 years. So this is a rapidly growing field, but it's also a field with not a lot of information or data. We can see there's some sort of seminal eruptions along the way here, and we see little bumps sometimes in the amount of studies related to that new information collected. The colors on the chart refer to the different types of impact studies that you can have. So there can be theoretical studies of what the impacts might look like. There's post-eruption investigations where you actually go into the field and observe past impacts. The same thing when you go into the field and observe it remotely. There's carrying out experiments to see what impacts might look like. And then there's a few other components, and they all come together to give us a rapidly increasing field. What I want to highlight here is that compared to other natural hazards, we're really starting from a very, very poor base or evidence base. So for example, for earthquakes, there are more than 600 post-earthquake impact surveys in the field. And for volcanoes, it's much less than that, but there's about 30 post-eruption impact studies. And most of those have happened only in the last 25 years or so. So we're orders of magnitude less information for volcanoes, and that means that our ability to forecast impacts is also compromised because of that. So just to zoom in a little bit more on the same data, so the number of impact studies published, and look at them as a function of volcanic hazards, we can see that tephra fall impact studies really dominate all of the volcanic impact studies. And that's, I think, for the same reasons I mentioned at the start, that we have tephra covering a much bigger area. And also it has quite a varied impact. It's less binary than people might think the flow hazards are, for example. And it also has some of the safest access. So if I'm going to look at impacts from an eruption, I would much rather do that with a couple of millimeters of tephra fall than at the bottom of a valley under an active volcano, for example. But most of our studies across all of the volcanic hazards are really less than 25 years old, and we don't have a lot of information on the impacts. And that's something we're improving and something I'm quite passionate about. But let's zoom in a little bit on the empirical studies. So by empirical, I mean the observational studies, where we actually look at the impacts from an eruption and we catalogue those impacts. And we use that to then forecast future impacts going forward. So these observational or empirical studies are quite a small proportion of the total number of impact studies. So up in the top here in this sort of beige, we've got our remote sensing studies, and understandably, they've not really come out until recently when we have easy open access to satellite data. And then we have these field investigations in the blue here, which is a bigger proportion, but still they make up less than 40% or a third of the total impact studies. And so I'm going to zoom in again and talk about just tephra fall and just empirical studies for buildings, so post-eruption field investigations to start with. And you may or may not be shocked to hear that there are only 4 published field building damage surveys for tephra fall. And we know that tephra falls affect many more buildings in many more eruptions than just those 4, but there's only been 4 published studies. I will add there's another one that's being written up right now by Vicky Miller at GNS for St. Vincent, but it's not quite published, so I can't include it yet. So we're averaging at the moment 1 published study every 8 years or so, which is not very much. So our data set of what does tephra fall impacts look like for buildings is really very small. The good news is that since the first one that was carried out in 1991 for Pinatubo through to Ambai, which was in 2018, the most recent one published, we've increased the number of buildings that we're actually assessing. So there's been an improvement in the amount of buildings that we can assess. So we are gathering more data as we go forward. But each impact assessment is completely different, and it gives us new information and has a different context and a different setting, different set of buildings. And if we look at the 4 studies, and Ambai has 2 different bars because there were 2 different damaging tephra fall stages for that. I'll come back to that later. But if we look at the buildings that are assessed on the y-axis as a function of the tephra loading or tephra thickness, you can think of them as synonymous. It's a function of the density of the tephra to convert between the 2. But if we look at the different studies, they cover different tephra thicknesses, but most of them are really focused in this less than 2.5 kilopascals, which is less than about 25 centimeters, give or take. So for these thick tephra falls, we really only have Rabaul 1994 to concentrate on. And I mean, maybe that's okay because the bigger areas and therefore the bigger number of buildings are going to be affected by the thinner tephra falls. So if we're going to bias our data, it's the best way to bias it. But it's still interesting that we really have no data in these larger thicknesses. So I'm going to focus in on each of the 4 studies in turn and just talk about what we learned and the context of those studies. And then I'll focus for the last part of the talk, I'll talk more about the Ambai study because it's the most recent and because I've just published it. So for Pinatubo in 1991, it's this little cube here. So it's really only a very thin range of tephra that was considered. And that's because it was only one location, one village, Castellijos. And this was carried out actually by looking at photos. So a medical team went out after this eruption and they took a lot of pictures of the buildings and they gave those pictures to structural engineers back in the UK, Robin Spence and others, and he assessed the damage from this eruption, remotely looking at the photos. So he assessed 51 buildings and he assigned them to 6 different damage states. So a damage state is basically a way of categorizing what level of damage there is. So if we have 6, it will go for damage state 0, which means that there is no damage at all, through to damage state 5, which is complete collapse and destruction of the building. And you iterate up through that basically with increasing amounts of damage. And this is really, as I said, it's quite a constrained amount of tephra, but we're looking at 1.5 to 2 centimeters of tephra, and you can see there's complete collapse of a number of the buildings in this town. So the main findings from this first empirical building damage study was that it actually set up this this way of categorizing damage into scales or states, and they ported that over from earthquake impact studies where they've been doing that for many decades. What they found is that the typology of the building, so what the building is constructed from and how it is designed and built, is really important in determining the level of damage. So you have the same tephra thickness across this town, but the building types are different, meaning that you have different levels of damage for each building. They found that the long span buildings, which means you have a wide distance between the vertical supports underneath the roof, or a long span roof with a wide gap between the supports, and a low angle roof, were the most susceptible to damage. They were the most likely to collapse, which you can see in the picture behind. This is a long span low angle roof here that's collapsed completely. So moving on to Rabaul, which was the next study in 1994, this is the one that really covers the range of tephra thicknesses. So it gives us this information at the very high tephra thicknesses. And this was carried out in the field by a physical scientist. So he was working, Russell Blong was working alongside an insurance loss assessor, and they were in the field looking at the impacts to buildings in terms of the loss or the cost of replacing those buildings. We have this range in thickness. The town they were looking at, Rabaul town, was much closer to the volcanoes than Castillejos in Pinatubo was. But again, they used this idea of categorizing damage. But instead, this time, instead of states, they considered the states as a function of damage indices, which is basically the proportion of the building that needs replacing. So if your building costs $10 and you have a 50% damage or a 0.5 damage index, then it's going to cost you $5 to repair it, basically. And this was the first time that anybody had tried to look at the costs from building damage from volcanoes. And it was the first time that anybody had discussed the idea of building volcanoes, having building codes that were going to make buildings more resistant to volcanic hazards. And what they found at these very thick tephra falls is that some buildings were really quite resistant. And that was a bit of a surprise. Typically, they were concrete or sometimes metal sheet, but they really withstood some very large loads, whereas others didn't. So moving on to Calbuco in 2015, there was a bit of a lull, notice, between the 1994 Rabaul and Calbuco 2015, so a 20-year gap in any damage surveys. Calbuco had a range of tephra thicknesses. It was mostly bunched in this sort of 30 centimeters or lower. And this was, again, making use of photographs. So the Chilean authorities, as part of their post-disaster needs assessment, took a lot of photos of buildings, and they carried out a lot of engineering assessments of the damage of the buildings. And then a volcanologist, Josh Hayes, looked at these along with the team and categorized the damage for the 417 buildings into 6 damage states. So DS0 to DS5, again, similar to Pinatubo. And we have a pretty wide range of tephra thickness, but not as much as for Rabaul. And this was the first time that anybody had tried to combine different data sources, but to recognize the data quality of those data sources. So for example, when you have an engineer assessing a building, and that provides information, you have a much more confidence in the assessment of damage than when you just have a blurry photo, for example. But we want to be able to use both of those data sources. And so Josh created a data quality index that tells you the uncertainty associated with different data sources so you can combine them appropriately. And what they found was that the buildings that were built to snow code, because this was a cold area at the bottom of Chile, fared really well under tephra fall loading because, of course, the building roof was designed to withstand horizontal or vertical loading down. They also found that the condition of a building, not just the type of it, but how well it was maintained and how old it was really important in influencing how damaged it would be as well. So moving on to the final published study, This is AMBI in 2017 to 2018. I'll spend a bit more time on this one because I was part of the study. We surveyed 589 buildings. We again assigned them to DS0 to DS5, but we had a pretty wide range in tephra thickness, but maybe not as much as at Calbuco. So this impact assessment that we carried out was during the crisis. So we were in the field while the eruption was ongoing. And it was carried out in collaboration with the Vanuatu Meteorology and Geophysics Division and part funded by the New Zealand Ministry for Foreign Affairs and Trade. So it was actually a study that was part of a wider coordinated humanitarian response to this crisis. We were looking at the potential for recovery and resettlement after people were evacuated. And this is now published recently in the last month or so. So if you scan that QR code, it will come up with the paper, or here's the citation. So Ambai is an island in Vanuatu. So it's in the northern part of the Vanuatu archipelago. It's sort of off in the South Pacific above New Zealand and off the coast of Queensland in Australia. It's elongated along a rift zone, and you can see there are a lot of tiny little scoria cones peppering the surface. There's sort of a Marp up here, and we also have some summit calderas from some explosive activity in about 400 years ago. So in 2017 to 18, the volcano produced a multi-phase, so different styles of activity over an elongated time of about a year. Eruption. It was part of an ongoing sequence of eruptions and unrest that have been ongoing since 1991. And it caused a number of partial and full evacuations, and there were about 10,000 people who live on the island. And the water and air quality were unfortunately compromised. This is the time scale of the eruption from start to finish. And the main things to point out is that there was a number of damaging tephra falls, the red triangles. And we actually carried out 3 different field visits during the eruption. And the last one is where we focused most on buildings. And it was carried out during the final full island evacuation. So this is an image that I took while we were on the last evacuation boat off Ambai. And so the authorities were very kind in letting us stay until the last possible point and then getting us off the island. So it meant that we were really time constrained in taking this assessment. And we were also quite conscious of the impact that the evacuation and the eruption was having on people. We surveyed 589 buildings across the island. These are the yellow dots here. There were about 250 or more that were damaged or destroyed. And we see these 2 main damaging tephra fall phases that impacted areas to the south, especially Red Cliffs, and to the east, over here in July 2018. The point of going out there was both to consider the humanitarian aspects, so there were people looking at water quality, air quality. We were also looking at the amount of buildings damaged, but also to collect data so that we could use these data in forecasting tephra fall impacts in Vanuatu, but also further afield as well. And one of the key aspects of this impact assessment was that we were collecting data on tephra fall impacts for these traditional buildings for the very first time. No one had seen damage to these or catalogued damage to these types of buildings before. So they're built using local timber and materials, and we see them across the South Pacific, but actually they're also quite prevalent in the Philippines as well. And this is a pre-eruption impact assessment that I carried out in 2014 or so. Now, this is a plot of tephra thickness with the surveyed buildings. And what I wanted to show is that the traditional buildings, the blue, really dominate in the thicker tephra fall areas. So where we have thicker tephra fall, there were many more traditional buildings. And in terms of damage, this time the colors represent the level of damage. We can see that with increasing tephra thickness, we see increasing damage, which is what we might expect. But there's a lot of variability in this study. In this story, sorry. So we have had surveys before, not surveys, theoretical studies before that have talked about when we expect collapse for these types of buildings. So Blong in 1984 said anything above 100 mil after this blue band, we might expect collapse to initiate for these types of buildings. And our pre-eruption study in the Philippines said that we would expect maybe about 10% to collapse below 100 mil, but the majority would be in this box. And what we actually found in Ambai was about 20% of these buildings were collapsing with tephra thicknesses of less than 100 millimeters. So why is that? The ones that were collapsing with smaller tephra thicknesses were typically long span. So again, a big gap between the vertical supports supporting the roof. They were shallow pitch, so the same story that we saw in Pinatubo. They were also older, and some of them were in very poor condition. So again, reflecting what was found in Kalbuko as well. The ones that didn't collapse, even though we had a lot of tephra full thickness on them, were where mitigation strategies had been employed. So here we can see that there was propping of the central beam that supports the roof. So if you do that, you add a lot of resistance to the roof and it can support a lot more load on it. We also had mitigation actions, like people would put tarpaulins over the roof, which means that the tephra sheds off much easily, which means the load is lower. And people were also managing to clean during the tephra falls to reduce that load buildup. So just to summarize, some of the benefits of collecting observational impact data are that we can really improve our understanding. Every time we go out and do an impact assessment, we learn something new, and it's something that we can transfer to other at-risk areas. And the more data we have, the more certainty we have. So we're not there yet, but this is an image of fragility curves. So the probability of damage with a function of hazard intensity. This is for ballistics because we don't have these curves with uncertainty for tephra fall yet. So this band here is showing the uncertainty in our estimate. And we want to be able to create these for tephra fall, but we're not quite there. Some of the challenges that we see with carrying out these observational impact assessments is that really the best data are going to be collected as soon as possible or during the eruption. And that's obviously not always possible or safe, and you're pretty much always going to be time constrained on that. You're rushing around and you have perhaps difficult access. There's always a context aspect here. You know, things change from each eruption and each setting and each set of building typologies. So we need to collect more data to be able to average out these differences. These sort of studies have to be done with the collaboration and the support of local scientists and populations. And that's not always easy to set up during a crisis because local scientists are often very limited and stretched at times of a crisis, understandably. And this last point here, post-traumatic stress disorder. Sometimes going out during a crisis can be really quite traumatic. This is some images from Ambai. These are my legs, and that's a kitten. And when they evacuated the areas, and there's a pig there, they weren't allowed to take pets or livestock. So they had to leave behind their pets and their animals. And that's obviously very traumatic for the residents, but it's also quite harmful when you're walking around and these animals are desperate for food. So, you know, there's teams going out. If you're taking out early career researchers, and even looking after yourself, I think there's an element here that needs more study. So my final slide, because I didn't want to end on a negative, is to say that there's some great opportunities here. So one very clear one is that we're more starting to use remote sensing to carry out impact assessments. So George Williams and others looked at the Kalut 2014 eruption and assessed 1,154 buildings remotely using Google Earth. Ellie Tennant looked at the St. Vincent 21 eruption. She managed to look at 2,000 buildings, thereabouts, using drone imagery. So there's some really good methods coming out, and the number of buildings that you can assess remotely is obviously much, much greater than the number that you can assess in the field. So there's a trade-off between those two types of data. We have lots of different moving parts when we do these impact assessments, and we need some guidelines and standardization. It would be nice to be able to do repeat studies in time to support and gather evidence for recovery, efficient recovery. We need to look at our uncertainties better, and there are so many opportunities from different disciplines to get involved in this sort of study. So thank you very much. I return on this slide.
Thanks very much, Susanna. That was another excellent talk. So we're a bit, just because of the delays we had at the start, we are a bit closer to the end, so we were a bit short for time for questions than I would have liked. But if you do have any questions, please either raise your hand and I'll unmute you so you can ask a question or put it in the chat. Maybe while we wait for any initial questions, I can ask one, which is for Kadek. So Kadek, you presented basically at different times of the year for each volcano, you assessed either high, medium, or low risk, from what I remember. Do those basically, depending on what the risk is at a given time, and you discuss some rather general mitigation actions, but if you're in a different risk state, does that trigger any particular mitigation actions to happen at that time?
Yes, I just measure the average of the race during all the time span for 30 years period, and from the mitigation plan that I suggest is most based on the general volcanic risk that mostly happen during that time. For instance, when the certain volcano erupted in a certain time, like Mount Agung or if Mount Rinjani, if they erupted during April to November, the wind gonna be the most important factor to blow up the volcanic ash to our Bali airface, and during that time there is no rain during that dry season. That's why the mitigation strategy is like to either giving the warning or either making the flexible flight route there. Yeah, that's all.
Cool. Thank you very much. And I also had a question for Susanna, which is, you mentioned towards the start of your talk that there's less information on volcanic impacts than for other hazards. Why is that? Is there a reason, like a known reason for that? It surprised me slightly.
Yeah, that's a good point. I think partly it's because volcanic eruption impacts are less frequent on populated areas than they are for earthquakes or cyclone or flood. But I think it's also partly the danger aspect. So it's much harder to go, once an earthquake's finished, you have aftershocks, but typically you can go into the area more safely than you can with an eruption that can last for like years and years. I think also we're a small field, right? Volcanology is small, and volcanic impacts especially is an even smaller field of volcanoes. So there's a few different factors, but it's a significant difference, right? And that's what we're trying to change.
Okay. Well, thank you once again to Kadek and Susanna for your presentations. That was they were both really, really good. And I certainly appreciated the chance to listen to them. Thank you for everyone else who attended today to listen in and give their time to listen as well. It's again really nice to see that we had a good number of us here. Hopefully we'll hold another one of these seminars probably in a different time zone in about 3 months. So it's probably about 6 months for it to come back around again for this time zone. So we'll hope to see a number of you at another one of these in the future. Cool. Thank you very much, everyone. Have a good rest of your day.
Paul. Thanks, everyone.
Have a good day, everyone. Bye. Some people. Bye. Thank you.